Hello guys, this is Prime Concept. And we have another problem to analyze under electric field intensity. And the question says a point charge Q equals this is located at the origin, right? At the origin of a coordinate system. Now, if I'll draw my solution diagram, say this, you have something like this. So this is our origin. So this is where we have this is where we have that charge at this point at the origin. So, and it has a value of -8. This is nano. So nano is times 10 to the power -9 coulomb. So this is where that charge is. A point charge of this is located at the origin, which is this. Find the electric field intensity. That is what it is. The electric field vector at the field point. Another name for field point is or field is your test. So test region or field point. So at the field point, x equals 1.2 meters. So this is positive x direction. So I'm going to draw like this. So this is my 1.2 meter, like this, right? Positive. And then y equals negative 1.6. So which is downwards. So I have like this, negative 1.6. So this is it. Now we're looking for the electric field at a point given by these two systems. So if you trace this, if you trace this, if you trace this down, because you have to draw your resultant to get that point. Let me draw. So like this. So this is that point. Let me call it point P. Even though I didn't draw to scale, the diagram is looking somehow. So I have this. If I trace this, I have this. So let me call this point P. Now, you should know that this distance is same as this distance, right? So which I'm going to do like this because both of them are the same. So this is still minus 1.6 meters because it's downwards. Now, let's consider this since we don't know the charge that is here, is always assumed to be a positive charge, a positive test charge, since you don't know it, because you're trying to find electric field that will be experienced by a charge which we don't know at this point. So the assumption is always a positive test charge. Now this is our source charge, which is negative. So a negative and a positive test charge, what kind of force will be experienced? It's going to be a force of attraction. Attractive forces are always attracted to the what? To the source. So it means my direction is going to be like this, towards the source. So this is just my vector diagram. So in order to find the electric field, of course, you should know that this is a two-dimensional problem. So it would involve the vector form of electric field. First thing I want to find is my vector R. So this is R. That's the first thing I want to find. I know this, 1.2. I know this. So I want to find R. Now for me to find R, watch. See, let's say I'm moving from this point. Let me move in the direction of this vector. So if you are at this point and you move upwards, you have your R. Say you are at this point. Another way you can arrive at this particular position is to move up, right? And then move like this. Now watch. If you move up, you are moving against this arrow. So it's going to be negative, right? Now, remember y-axis, you denote it with your J. So if I move up, it's going to be negative. Now remember, this is already carrying negative. So negative of negative 1.6 J, right? Then when you get to this point, you move like this again. So this is still going to be what? You are moving up against this arrow. So it's still going to be what? Negative. So you have negative 1.2 I. If you rearrange this in a standard way, you have that your R is, want to put this first, negative 1.2 I. This becomes what? Positive 1.6 J. So this is our R. Then let's get the unit vector. Our unit vector is given as this, which is R over magnitude of R. Right? Now I'm going to find the magnitude of R. The magnitude of R is simply this square root of minus 1.2 square, 1.6 square. So if we punch this, let's see 1.2. So if you punch this, you get 2. So we don't waste time. So if you punch, you get 2 meters. So that is the magnitude. Now, what is our unit vector going to be? Our unit vector is simply going to be minus 1.2i plus 1.6j divided by what now? 2. So if you still solve this quickly, 0.2 divided by 2, this will give us negative 0.6i plus, let's say, 1.6 divided by 2. So this will give me 0.8j. So that is what I have, right? Let me rub this part so I can have space. So the next thing I want to find is the magnitude of the electric field. E is going to be kq by r squared. So 9 times 10 to the power 9 is k. Q is what now? Remember, you don't consider the sign. Since this is actually magnitude, you're getting the magnitude of E before you introduce the direction. You don't consider this sign when you get solving for this magnitude. So you have 8 times 10 to the power minus 9. So divided by R. What is our R? So what is our R magnitude? Is 2 squared. So if you punch this, this would give us 9 times 8 divided by 9 times 8 divided by 4. So this would give me 18 Newton per coulomb. 18. Yeah. Now we are not done because we need to include the direction. So the next thing I want to do now is the E vector. The E vector is simply going to be this, which is 18 into this now, which is minus 0.6i plus 0.8g. So which is that. So if you punch this, you will have, this is going to give us 10.8, okay, minus 10.8i plus 14.4g. So this is what we have. This is what we have as our final answer, Newton per coulomb. So this is the electric field vector that is asked or required in that problem. I believe this concept is very simple and clear to you. Please do well to subscribe to my channel, like my videos, and share with your friends so that they can also benefit. I'll be solving more problems. In my next videos, I'll be doing more topics. The next topic I'll look at is electric field lines, right? Or lines of force. I'll be handling that, and then we'll proceed to cover the course electromagnetism. Thanks for watching. Remember, this is Prime Concept.